it.
Eh?
Still, I've clicked on it.
You clicked on it. Okay. All right, I
I've
should stop
clicked
talking
on
then. All right. Please make me co-host. Thank you.
it. Uh,
And start once you see that it has started live streaming. I've not seen any notification that it has started live streaming here though.
Still loading. Internet is unstable.
Eh? Okay, it's been live streamed. Okay.
Hello, welcome everyone. Welcome to the live coding session day 3. Let me make just wait a few minutes for us to. Right, welcome. I can see Limbola.
Yeah, good evening.
Yeah, welcome.
Thank you.
I can see who else is on the call. Yeah, I can see Ade, brother Silas. I don't know if we have any sister Silas too. Okay, just brother Silas. We have Christian, Utsu, Captain, Michael, Elechi, Kenneth, Nina, Oluwa, Oluwadara. Yeah, I think I got that. Reginald, Vara, you're welcome. Toluwani, Vani, Boma, Excel, Praise. Yeah, nice to have you guys here once again. Today is the third day for the live coding session of Stage C Data Science. And today we are basically going to be looking at multi-classification. Yeah, it's going to be probably similar to what we saw in the first class, but yeah, I'll emphasize more on it. Then just before we get in our last class, we actually went through some more well, let's say advanced projects where we saw the different metrics we can use in calculating, sorry, to measure the performance of our model, the accuracy, the precision, the score, the conversion metrics, and the rest of them. So we actually went through that in our last class, and it was an interesting one to know how those metrics can help us track the performance of our model. All right, so today we're just going to look at multi-classification, and we're going to be using the Iris dataset. But as usual, we'll just go through some slides and then we jump into into the notebook. All right, so let me just share my screen. Can you guys see my screen?
No, please.
Hello, can you guys see my screen?
Yes, not yet.
Yes, not
No, we
yet.
can't see your screen.
Hmm? Should be showing. Just give me a sec. Is it showing now?
Not yet.
No, we can say your screen. Oops.
Okay. How about now?
Yes, we can
Yes.
say it now.
Okay, multi-classification. The stage C, it's just centered around classification, right, in machine learning. So that's why it's just basically the breakdown of course content. So today is multi-classification, and my point is, it's in our previous two class. It's just that addition of an extra. It's like the name implies multi-class. So here we are not just trying to classify, let's say, yes and no, or maybe true and false. Or like in our last class, people that purchased some an item and people that did not purchase, it's more like a prediction out of the excuse me. So that's just the difference, but every other thing remains the same. Get to the class and then you just get into it and split your data sets, and yeah, the difference is just going to be probably the machine learning and your output. That's just it. All right, so um, so for the first slide is just an introduction to what we are trying to talk about. So the essence of this multi-class classification, it's beyond dealing with two distinct categories. So it navigates more complex landscape of multiple categories. This complexity mirrors the real world more closely, where entities are often more than just two groups. So we have the binary and versus the multi-class classification. The binary is the one I just mentioned. It's like when you have just two classes that you're trying to classify, right? So the leap from binary to multi-class classification is not just about adding more class, it's about scaling complexity and adapting our strategies. So while binary classification focuses on distinguishing between two outcomes, multi-class classification requires a more nuanced approach to handle multiple, often interrelated categories. So the application of multi-class classification are vast and varied. In healthcare, it powers systems that diagnose disease, categorizing conditions into multiple types. In retail, when it's a retail, like a retail industry, people that do business or people that are more related to sales and the rest, it helps in classifying products. Then in the digital world, it underpins algorithms that recognize speech, categorize news articles, and much more. So why does it matter? Understanding multi-class challenges, it enables us to develop models that reflect the complexity of human categorization, enhancing the accuracy and relevance of our prediction. That's why it actually matters. So if we take a closer look, multi-class classification extends beyond the principle of binary classification, right? It goes beyond to three or more classes. So that's just like I said, the physical difference. And considering that we are looking at more than two classes, we're likely going to be encountering some challenges. And one of the primary challenges in multi-class classification is how to extend algorithms that are inherently binary, such as logistic regression or support vector machines to effectively handle multiple classes. So what it's saying in essence is most of these models we are working with they were already designed to work with just two classes. So if we are going just beyond two, we need to be able to tune it or adjust the necessary things we need to adjust to make it adapt to the multi classes. So these challenges is not just technical but conceptual, pushing us to rethink our strategies for separation and classification. So extending binary classifiers and yeah, you just go beyond the binary classifier. So why understanding matters? Foundational knowledge. A deep understanding of multi-class classification is foundational for anyone venturing into machine learning. It equips us with the knowledge to choose the right strategies and algorithm for a specific problem, ensuring our models are both accurate and efficient. Strategies for multi-class classification. We have the one versus OR strategy, one versus US strategy. So the one versus US strategy, also known as one versus all, simplifies multi-class classification by breaking it down into multiple binary classification for each class. So let's say you have 0, 1, 2. So when they say one versus all, it's like picking out one, matching it with, like sorry, picking out 0. Again, let's say you have a class, three classes, 0, 1, 2, or maybe high, medium, and low. So what this one versus all does is it picks out, let's say, high, match it with low and medium separately. After it's done, it picks out, let's say, medium, match it with high and low. Then once it's done, it just pairs it up. That's how it says it gets it down to multiple binary classification. So for each class, a binary classifier is trained to distinguish between that class and all other classes combined. So it has some advantage. I mean, the one versus the rest, one versus all, which has some advantages. It's actually straightforward to implement and interpret, making it an interactive option for many multi-class problems. Then the challenge is a powerful strategy. It can struggle with imbalanced data sets. I think in our last class we saw that the data we were using were actually imbalanced, which was what made our recourse score to actually reduce. For I think the class of one actually reduce. Yeah. So that's just the challenge. We have the one versus one strategy. This approach takes a different tack by creating a binary classifier for every pair of classes. So if there are n classes, this result is n, then n minus 1 divided by 2. Formula is kind of a bit complex. But yeah, the class is predicted by aggregating the outcome of the classifier and choosing the class that wins the most rows. So it's like a competition, which after at the end of it all, it brings out the ones that maybe score better. We have algorithm for multi-class classification. We have decision trees. I think this actually most of these are going to be seen in our last class. We'll actually take a look at other kind of models, and if necessary, we can see how it works in the pipeline. Hopefully. So we have decision trees, random forest, naive Bayes, and neural network. The decision trees are a non-linear predictive model, for those of us that are not aware, that recursively splits data into branches, making them naturally suited for multi-class classification. So each node in the tree represents a feature in the dataset, and each branch represents a decision tree. So one of the main advantages of decision tree is their interpretability. They provide a clear visualization of the decision-making process, making it easy to understand how the model classifies. We have the random forest. We also have the naive Bayes. So most of these models, we're actually going to be seeing how they work in our last class. But yeah, you can actually use them for multi-classifications too. I hope you guys can hear me. Hello, can
I
you
don't,
guys still hear me?
I don't know. As you're talking, your volume gets lower. But you ask
Hello.
this question. Ah, can you hear me?
Yes, I can hear you.
Yeah, I can hear you. I can hear you. Okay, I think my network is actually bad today. Hello, can you guys hear me now?
Yes, I can hear you.
Okay. All right. So we have data preparation. It's just the usual process, making sure the data is clean and they are all accurate and ready for processing and yeah, for the model actually. So the crucial first step is data processing, which involves cleaning and transforming the raw data. This is just the requirements you just need to put your data in, more like what you need to do before you start reporting classification. So we all know this. It's basically preparing the data. You do some feature selection. Maybe after checking maybe after plotting the correlation between the features you have and the target, you can manually decide to drop the ones that the correlation is probably not high. But then again, you are likely going to drop maybe columns that would play an important role in decision making. But yeah, feature selection is also involves identifying most relevant features for our model, reducing dimensionality, and improving model performance. We also have feature engineering. Maybe you can generate some columns from existing data or existing feature, or maybe you get an external data to enhance the model. Then we all know that if maybe, like I said, maybe what we are trying to classify is high, medium, low, we will need to turn it into numbers so that the model can understand. So this is where your one hot encoding transformation comes in. Then you also need to handle imbalanced data, especially in class imbalance. So you need to make sure that the classes are balanced, right? So imbalanced classes occur when some classes have significantly more samples than another, and it can lead to your model being biased because you are training it more on one compared to the other one. So you just need to downsample it, and this whole data preparation is actually necessary for good performance. Then we have the evaluation metrics. Yeah, we saw this in our last class, the accuracy, right, which measures the proportion of correct predictions among the total number of cases evaluated. And we also know that this accuracy can be misleading at times. Like we saw, yeah, I think everything practically was in our last class. I wish I could open the notebook. So accuracies sometimes can be misleading. You could have a high accuracy, right? But then again, if you don't check your maybe other scores, other metrics, right? You like the one we did in our last class, you won't have known that the recall or maybe the other classes that it was trying to classify is actually low. Let me see if I can open it. You won't have known that it's actually low. So yeah, accuracy can be misleading. It can be misleading. So don't just dwell on it, right? So we have the precision recall and F1 score. We talked about all this. So precision measures the accuracy of the positive predictions. That's the number of true positive divided by the number of true positive and false positive. So it's the one that is correctly predicted over the whole positive let's say, count, while recall is the ratio of correctly predicted positive observation to the actual positive, right? So we have the F1 score, we have the macro, we also saw this in our last class, the coefficient matrix too. This is actually the visual that can show you, okay, this is what is classified correctly, this is what it did not classify correctly, then you know where and where you need to improve on your model to better perform well. So evaluation matters a lot. Yeah, it matters a lot. And we also saw why it matters in the medical industry, right? If you don't look at your recall score, you are probably going to be classifying people that has disease as maybe as false. Maybe you are saying that they don't have the disease. So you need to check out your recall score. We also looked at the finance industry where F1 score was of importance. You know, F1 score is like a combination of recall and the precision, right? It's just how you used to balance what you need to know. You used to know if it's balanced. So all these metrics are actually important, and we talked about it in our last class. Then we have implementing. This is the practical aspect. So let me take that to lecture. We are going to jump into the so yeah, just the normal procedure. Then we have the data set like I talked. It's the very first class. Data, data, and evaluating it to know how well it's performed. All right, this is where we conclude on the slide so that we can just get into the next group. Right. So multi-class classification entails and goes beyond binary classification to address real-world scenarios where outcome can belong to three or more categories. We saw the different strategies, the one versus the rest and one versus one. We saw the data preparation. This is where you basically just make sure that everything is in order, cleaning, outliers, you handle all those things, and then you evaluating the results you get from the model if they are performing well, how or probably for your use case, like I said, because most times you're not using model like to do something general. You want to use it for a specific industry. So there should be that metric that you're actually watching to know if it's doing well or not. So yeah, let's model focus we have there. Does anyone have any question on this slide before we move in? Any question? Okay. Let me check the chat box. Oh, geez. Hello, is it just Brother Silas or can any other person hear me clearly? Hello, can anyone hear me?
Yes, we can hear
Yes.
you.
We
All
can
right.
hear you.
All right. Okay, so here is the code we have. So like I said, it's just the same whole process in terms of classification, but yeah, we're looking at more than two classes. So the usual we import our models. I actually checked online, just so you know, the iris data set mostly, I think it's actually that it has that length of 150, not beyond that. Unless maybe I've not seen the one that's beyond that, but so far the one I searched online, they actually got 115 length. Okay, so making use of the iris data set. It has 3 flowers. Let's look at the description. It has 3 flowers in it. So we have 150 rows. I'm just trying to explain the data set because the last time we went through this, we did not get to explain this.
Hello,
So
please,
we have
can you zoom your screen?
okay.
That's better. Thank you.
Okay, so this is where we load the data set, just in case you're wondering. It's from our SQL library. We import the iris data set. Okay, let me see if we have any other one first. Hold on, I'm coming. We could have the Boston data set here too. Okay, so these are the different data sets we have inside SQL. So it's not just the iris, right? So it's just that the example I'm using the iris data set, but we have other ones, diabetes, digits, and the rest of them. So you can always take a look at it. Let's say load files. Sorry. I don't think it can work that way. Container path. Which one is different? Let me try the breast cancer. Okay. So this is just another data set that is inside SQL. This one is about breast cancer. That's 569 rows. So my point is you can access some inbuilt data sets in SQL. Right? So all you need to do is just import it and load it this way. Then you can access the description of the data set through maybe accessing it through this key. All right, so back to our iris data set. That's a fine. Yeah, it has 150 rows, 4 basic color, regional. We have the summary statistics. So this is just like you would do just to describe. Then there are no missing values. This is the class distribution, the owner of the data set, just some more details about it. So that is how you can actually access. If you actually just run iris alone, you can actually see some other features that you can get. You can also get the target name. I think that's just it. Let me do something like this. So we have the data itself, the target, which is actually what, let me push this down, or let me put it down. So you have the data, which is actually what we assigned to our X. We have the target, which is actually what we assign to our Y. We have the target name, the description, the features name, the file name, and the data module. So yeah, you just in case you want to access any of this, you just call on iris, then you pass it in a square bracket. So that's just how you can access some of the features here. So that was how we were able to unpack the data to X and unpack the targets to Y. Let me run this. So let's see what the content of X is. So X is an array. It's an array. So this is just the first four rows inside that X value. So let me do this first so that we know what we're working with. So iris picture names. Sepal length is the first one, the width, then the petal length and the width. Those are what they represent respectively. Right, I'm just trying to match this to this. So as they are arranged, here is just how these values are represented respectively. So this first one is the sepal length, the second one is the sepal width, then this one is the petal length, this one is the petal width. Right, so this is just the first four rows of our data set. While our target, which is the Y, uh, can anyone hear me? I think my network is breaking. Can you guys still hear me?
Yes, I
Hello,
can hear
can
you.
anyone hear
I
me?
hear you and see you clearly.
Okay, okay. Right, so this is just the contents of our Y, which is our target. So yeah, we are trying to, you can see there are three classes here, 1, 2, and then 2, right? So let me get the target name. So we have the Setosa, vesicolor, and Virginica. Hold on, change. Okay, 0, 1, 2. Yeah, 0, 1, 2. So the Setosa is actually the zeros. The vesicolor is actually the ones, and then the Virginica is actually the twos. So yeah, these are what these values represent, just in case you are wondering what they represent. So yeah, this is just how this data set is, right? But then again, yours could be probably obviously or most time going to be at this kind of level. When I mean level, like it's going to be a string. So it's now left for you to, convert it to numbers. You can assign months depending on how you want to do it, but you will be the person to know which one is one, which one is two, which one is three, but you have to convert this to a number, right? And it also depends on the model you are using. So yeah, this is what this represents, right? So this is actually where we are splitting it. This is where we are splitting it. We are splitting it 80 by 20. Let me adjust this to say 25. Let me adjust this to 4. So we are splitting the data sets into training and testing. It's 75 and 25%. Then this is where we load our model. Okay, and we make some predictions. So this is the predictions. Let's see what our X test looks like. Oh, sorry, our Y test, not X test. I think it's perfect again. Everything looks like it's matching. Everything looks like it's matching. Okay,
Except the
but
1, 2,
then
3,
this
4,
is just
5,
a
7.
manual way of looking at it. But we have, what did you say? Okay.
I
I
see
think I
except
see what you're
7
trying
to
to say.
There are one or two differences.
Yeah, I've seen one of it here. That's I say this is just manual way of doing this. I mean, obviously you won't be doing this for a very large data set, but I just wanted us to print it out because it's small. But this is actually what your accuracy is there for. It tells you how many was correct and how many is not correct. So you can see that the accuracy is 0.97%. So it's trying to say that out of all this, 97% of, sorry, out of all these ones, the 97% of them is correct, is exactly what is here, right? So our accuracy is 0.97%. Then this is a classification report to see other scores like the recall, precision, and the rest of them. So we can see that the recall for this is actually 1. So it has a low recall score on classifying those with ones. Like it had a low risk score. So yeah. F1 is just the balance of these two. We have the accuracy 0.97. There are 38 entries, if I'm not mistaken. Yeah, there are 38 entries. So let's see completion metrics. So this is actually different compared to the last time we looked at it that everything was so perfect. So here now, I think we should just look at it in that visual form. Here now is actually saying that what is happening? Oh, Seaborn is not here. Oh, sorry. Okay, so what it's saying here in essence is that um, right now it's classifying this vesicolor, one of it as Virginica, right? That's what it's classifying it as. Classifying it as a Virginica flower. That's the only one it got wrong. But yeah, obviously our data set is small, right? Our data set is small. But then this is our completion matrix with the true positives and the false
So on that this thing,
positives.
which is the predicted and which was the
And it's
actual
just for
on that
individual. You
C1?
won't probably read it the same way you do for the other one because those ones are just four. The actual are the diagonals. So where it says setosa, setosa, it means it predicted it's setosa, setosa. This one now that I have here, it's saying that this vesicle, the left hand side is actually like, will I say, okay, let me know before I make my statement. Right, so we have vesicolor is actually 8. Vesicolor is the ones with ones. Please hold on, let me just confirm that. Yeah, basic colors are the ones, right? And from our classification reports, we have 8 of them. We have 8 of them. But here now, you can see that it's 7. So in essence, it classified the remaining one as this flower. Do you understand? It classified this vesicolor as this flower.
Is it telling me or has it gone off?
Same here. Can't hear anything.
Yeah, guys, please hold on while your tutor tries to get back here. Yeah, he has lost
Okay.
his connection. Yeah.
Hello, can you guys hear me? Hello? Hello, can anyone hear me?
Yes, please. Can hear you.
Uh, I'm so sorry about that. My network kicked me out. All right, so we're almost rounding off. Let me just share my screen so that I just conclude what I was saying. And if you have any questions, yeah, sorry about that once again. Can you see my screen? Can you see the confusion matrix?
Yes, we can.
Okay, so yeah, I think I was just explaining that if we have, say we had one here, had it been we had one and one here, what it's saying in essence is that it's classifying this Setosa as maybe this vesicle or Virginica. That's what it means. But right now, everything looks correct except for this one that is classified as Virginica. So overall, if maybe you had up to 4, 5, 6 classification, you're just going to have one more matrix, right? So how you just interpret it is the diagonals are the correctly predicted ones. Then every other ones that falls on the other sides, either sides of the diagonals are just the ones that are misinterpreted as you just need to reference them. So like this one, as for example, it was misinterpreted as this flower, which it is not, right? So that's just
Yeah, yeah. Hello, what I was asking was if the left hand is it the predicted and the left side and the horizontal. Okay, the vertical side is it the predicted value, the horizontal the actual values.
in the confusion matrix.
Yes, yes, yes.
Okay. Um, I'm still trying to understand what you just said. You're asking, are you
Okay.
referring to the levels or the numbers inside the confusion matrix?
No, not the number. So in like
Mhm.
you
So you're
you
asking
have
if
the
these sides
vertical.
are the actual and this side is the predicted. Is that what you're trying to say? Is that what
Yes,
you're trying to ask?
exactly, exactly, exactly.
Okay, okay, okay. I understand you, but then again, I think the best way to put it is if you are trying to read, let me put it this way, but I won't say, I don't want to say this is the predicted and this is the actual because it won't really blend in well because we're not looking at numbers, we're looking at literally the same names. So how I'll put it is when you want to read the confusion matrix for more than like multi-classification, just go from your like from the left hand side to the right hand side. Like use this ones, reference this one as the actual ones, then you can reference these ones as the predicted ones. So I think in essence, it's just the same thing I just said. So yes, these are the predicted, these are the actual ones, and these are the predicted ones, right? So just reference this, moving to the right hand side. Anyone that falls out is just, yeah. You're correct. You're correct. Let me not dwell too much on that. Any other question for me?
Oh, yeah, on the confusion matrix, right? Can
Any
you,
other question?
yes, I'm asking a question actually on the confusion
Okay,
matrix. Yeah,
I can hear you.
okay, thank you. Um, is this not about the correlation between these features that we are having, meaning that obviously the Setosa feature will correlate highly with the Setosa feature if we are having these two data sets in some sense? Is it not some sort of correlation?
Um, okay, if I get your question right, you're asking if these values won't, is it not going to be similar to correlations, or is that what you're trying to ask?
Yes,
Is that
that's
what
the
you're
question.
trying to ask?
Yes.
Okay. No, it's not. Though we all know, yeah, we all know that confusion are looking similar to this, but no. If you are aware, when we talked about correlation, it's usually in a range of 0 to 1. Sorry, from -1 to the -1 to the +1. That's just the range for correlation. So if you have just this alone will tell you that this is not like correlation, right? This is different from correlation. So correlation falls within this range. So it's very different from this one. Do you understand? But it's just that they
Okay.
use heat maps to plot the visual. Yes.
Okay.
Any other question? Yeah, I'll share the notebook. Does anyone have any question? So let me just stop sharing and then I'll share my notebook. I'm coming. Let me get to the notebook link. So yeah, I'll just allow you guys to have some minutes to copy it. Oh, I'm not. Hold on, let me give the access to it. Okay, so I'll drop it on the in-call message. All right, so I'll just give us, I think, the remaining 2 minutes for us to pick that up, and then we can call it a day. So yeah, in our next class, while you are getting the notebook link, I've dropped it on the chat section of the call, so just get it from there. In our next class, we'll actually be looking at other classification modules. I mean, we'll touch some of them and see how they also work. So that will be what our next class would be, and yeah, I just hope to see you guys there, and it's going to be interesting. And you can come with any other questions you may have. Okay. All right. I think that's it. In the absence of no question, thanks once again for coming. I'll see you in the last class. Bye, everyone.
Bye.
Bye.
Right.